Okay, apparently I skipped over page 12, so I'll add that video underneath. So we have some properties of continuity, similar to the properties of limits on page 57. So if two functions are continuous at a point, then if we multiply the function by a number, it's still continuous. If we take two functions that are continuous and we subtract them from each other, the result is still continuous. If we multiply them together, they're still continuous. If we divide them, they'll be continuous as long as g of c does not equal 0. If that equals 0, then it would not be. And for a composite function, f of g of x, it should be continuous, but it might have some restrictions to it. Some functions that are continuous at every point in their domain. Now this is a little bit tricky. It doesn't really come up, so don't let it worry you too much. It's not really something you should spend much time thinking about. But polynomials. Polynomials are continuous everywhere. Rational function. Now you might think, well, a rational function has a vertical asymptote or a hole, and so it wouldn't be. But when you this is just saying within their domain. Like I said, we don't even really use that. I don't know why it's there. This is on page 73 of our textbook. So on the domain part, it's fine. A radical is continuous on its domain. Trigonometric are continuous on their domain. So sine and cosine definitely the whole way. All the other ones have asymptotes, tangent, cotangent, secant, and cosecant. But for the parts where the domain exists, they are continuous on their domain. Okay, so given number 2, if we took this polynomial and subtracted a trig function, that would be continuous. Okay. Now, this is important. This is usually a point on the AP exam. At least there are a couple different, it's called an existence theorem, and there are 3 main ones. And one of them is usually on the AP exam. So suppose f of x is continuous. Now that's important. It has to say that it's continuous. If it's not continuous, then this does not necessarily apply. So if k is a number between f of a and f of b, so that's a y value. So the function is continuous from a to b. So from the x values, from a to b, it's continuous. K is a number between f of a, which is the endpoint, the y-coordinate of this endpoint, and f of b is the y-coordinate of that endpoint. There has to be at least one number where in between a and b where f of c equals k. All right? If f of a equals 2 and f of b equals 5, then there has to be some place in between there where it equals 3. If it went from 2 to 5, it had to be 3 somewhere. So here's an example in real life. So a person was 2 feet tall when she was 1 year old. 1 year old. And she was 5 feet tall when she was 14. That means at some point in between there, she had to be 4 feet tall. She couldn't have skipped over any heights in between 2 feet and 5 feet. The intermediate, in between, intermediate means in between. The intermediate value theorem says you have to have all the values in between if you are continuous. So hopefully that makes sense. All right. Explain why the function has a 0 in this given interval. So what you can do here is if you test f of 0, so f of 0 is -1. And then if you test 1, f of 1, that would be 1 plus 1 minus 1, that's 1. So, first of all, you need to say that it's a polynomial, and since it's a polynomial, it's continuous. Now that we know it's continuous, we know that we have to have all the values in between here. All the values between 0 and 1 have to exist. So since it started out at -1 and it ended up at +1, that means, so -1 is less than or equal to f of x is less than or equal to 1. So by the, and we just usually abbreviate that, intermediate value theorem. So by the intermediate value theorem, f of x equals 0 for some x, and we just say equals c. Some value in between there. If at 0 it was -1, and if we ended up at +1, we must have passed to 0 because polynomials are continuous. Now, this part is key. A lot of students lost this point because you need to show the boundary, show that it's bounded by these two numbers. That's a very important part of it that gets left out a lot by students. When I've graded AP tests twice. I graded them last year. We graded from home, and then I graded them back in 2016 in Kansas City. So that's a problem that a lot of students leave out. Use the intermediate value theorem and the bisection method to estimate a 0 for this. Now usually we don't deal with exponential functions until chapter 5, but we can handle it here, so we'll go ahead and do it. So f of 0, that would be e to the 0 minus 0, and e to the 0 is 1, so that's equal to 1. Then if we tried f of 1, we would have e minus 3. So I don't know, you should know, maybe e is 2.7. E is approximately 2.71828, who was president in 1828. And that president served 2 terms, 1828, 2-term president, Andrew Jackson, and then a right isosceles triangle, and then ... Okay, I don't know it farther than that, but you don't need to know it that far. I'm just showing off. Actually, what is that showing off? Not much. All right, so the point is 2.7 minus 3 is going to be negative. So I know that since it's positive and it's negative, somewhere in between here it passes 0. So the bisection method means cut in half. So you're going to go halfway to 1/2, and you're going to plug 1/2 in there. Now, I'm just going to let you know on the calculator we could do that, and that's going to be 0.149. Okay? So that's still positive. So I know that my 0 has to be in between here. So then I would bisect this with 3/4, and I would find that. And if that was positive, then I know that it's in between these two. And if it was negative, I know it's in between these two. Now, we have our graphing calculators today, and that's going to be it. So that is good. And you're not going to have to do anything that far.